So in this video, we're going to be talking about how to solve first-order linear ODEs. But this time we're going to be looking at the case when we've got variable coefficients going on. So if you remember in the last case, we're looking where the constants in front of like the functions and the derivatives were, or the function was constant. Okay. Now we're looking at the case where the constants and like the coefficients are going to be functions. Okay, dependent on t. So we've got this case. This is how we kind of write it in the general case. We've got the derivative isolated on one side, and that's equal to something involving y and t on the right hand side. Okay, and then I'm just going to rearrange it to get everything involving y on one side, and then just leave kind of like effectively a function on the right hand side. So just basically I've just rearranged that like that to get everything like the derivative and the function on the same side, okay? And then I'm going to talk about how we can solve this. Now the thing is, wouldn't it be good, I'm going to look at this, okay, and wouldn't it be good if we could get rid of, say, like that term? If we could basically get rid of that term, so then all we'd be left with is something like the derivative is just equal to some constant, okay, or something that looks like that. So effectively, if we could just get rid of this middle term in here, that would be so good, wouldn't it? Okay, well, as it turns out, we can do that just by choosing a very, very special function. And I'm not actually going to go into the details of why it works. Perhaps I'll do another video on why this function effectively makes this disappear. It's effectively to do with the cancellation. It doesn't take long. It's just a little bit of algebra. But if you're interested in that, it's definitely worth checking out my other video. But for the moment, let's just see kind of how it works. So basically, we want to select a function. Select a function. I'm going to call that function mu. Okay, and I like to call this a fudge function or a fudge factor. So effectively what I'm doing is I'm choosing a function in such a way such that I can effectively just get rid of that middle term in there. Okay, and basically I want to choose it in such a way such that, like I say, when I multiply through by this function, okay, so multiply every single term effectively by this function, okay, equals mu q of t. So I'm multiplying every single term. That when I try and solve this, then this just gets rid of it, because effectively you get a cancellation going on, which just effectively get rid of this this function in the middle. Okay, which is quite cool. All right, and basically the way which I want to do that is I want to basically get rid of this function by choosing it such that the derivative of this function, so d mu by dt, because mu is a function of t, is just basically equal to this part of the function. So p of t times mu, I'm going to write this out again, mu p of t, or it doesn't matter. No, actually I wrote it, sorry, indecision. P of t times mu, okay? And the reason for that is if you have a look, I can rewrite this, just a very quick reason. I'll do a more thorough reason later on in another video. If I rewrite this as d mu y by dt, well, then effectively I can just break that up into, by the chain rule, effectively by the chain rule, this is the derivative of mu y with respect to t. I can, if I just treat this as a fraction, I can just multiply through by mu, right? And so I end up with this. Well, then I can end up, by the chain rule, I can end up with d mu by dt, okay, and I can end up with plus dy by dt. So in other words, the derivative of, if I just maybe write this out a little bit neater, dt, this is mu and y, effectively I end up with d mu by dt, which is mu and y, of mu y, is equal to the derivative of mu times y, okay, sorry, I forgot that bit. Yeah, so the derivative of mu with respect to t times y plus mu times the derivative of y with respect to t times mu. Okay, that's just the chain rule, right? Well, then if I choose my function in such a way that d mu by dt equals p of t times mu, then effectively I can just replace that with p of t times, times mu, yeah, times mu. Well, that thing effectively would cancel with this thing here. Okay, because that was effectively equal to this mu times dy by dt. So therefore, when I substitute it back in, effectively these two things will just cancel through. Okay, and I'll just be left with mu dy by dt equals that. Okay, that's just kind of a very quick, rough argument as to why that should work. Hopefully you follow that. Hopefully you followed that. If you haven't, don't worry. I'm going to do a more thorough video of why it works. But that's just a very, very quick reason about why it should work. Okay, so effectively the idea is that I want to choose a function such that that is the case. Well, what is that mu function going to be then? If that's the case, I will end up with again, I'm just going to isolate mu's on one side and everything not involving mu's on the other. So everything involving t's on the other are a constant. Okay, so I'll end up with mu on this side, which is 1 over mu d mu by dt equals p of t. So I've just divided through by mu. Then I'm just going to get rid of this dt by multiplying through by dt. Okay, and integrate both sides. Right. So what am I going to end up with? I'm going to end up with the natural logarithm of mu equals, we're just going to end up with the integral of p, whatever my function p is, with respect to t. Okay, so I'll basically have my constant coefficient here, or not my constant coefficient, my variable coefficient here, okay, that when I integrate it, it'll be equal to that, and I can just do a little bit rearranging, so I end up with mu equals e to the integral of p of t times dt, and of course there will be, that's fine. Okay, so that is what my function is going to be equal to. Yeah, and notice that there's no plus c because I've basically still got the constant included in that integration. I haven't integrated that yet, so I still have a constant of integration which comes along for the ride when I integrate that. Okay, and in actual fact, we don't end up putting a plus c here, just purely because we're completely in control of this function mu. Okay, we are choosing this function mu. Yeah. If you notice, there's no mu given to us in this equation. So in other words, we've introduced mu, so therefore we're completely in charge of what mu is going to look like. So I'm going to basically say, for convenience, let's just get rid of this plus c. Let's just say that the constant is 0. Yeah, because I can do that. Yeah, I'm in charge of my function. The function hasn't been defined in the equation. It's not been given to us in any way, shape or form. I've come up with the function. It's a completely arbitrary function, and I've kind of deduced what the function is going to look like, but because I'm completely in charge of the function, I'm just going to basically say, do you know what, I don't want a plus c there, so I'm not going to keep it. Okay, so this is basically what my function is going to look like. So, basically I want to try and find a function that looks like that. So I basically look at the coefficient in front of the y. I look at this coefficient, I raise it, I integrate it, and then I raise whatever the integral of that function is to the power of e, okay, or e to the power of that function, and that will give me my integrating factor. So let's do an example. Let's do an example and kind of see where it gets us. So let's say, for example, we have ty dash, so I'm going to change that to dy by dt for you guys, dy by dt minus 2y equals 5t squared. Alright, so that's essentially what I've got, okay. So, first things first, I want to get rid of this, in general. If you look at the general form that we had up here, there was nothing in front of this, or there was a 1 effectively in front of this dy by dt. There was no coefficient in front of this dy by dt. At the moment, there's a t. So the first thing I want to do is get rid of this t. So I'm going to have to divide through by t. Okay, so first thing says I'm going to have to divide through by t. So I'll end up with dy by dt equals minus 2 over minus t over 2y. Minus t over t, 2 over ty equals 5t squared over t. So effectively that just becomes 5t, right? That's fine. So now I've got it in the form of dy by dt equals p of t, plus p of t times y equals q of t. So what is everything? So p of t, my coefficient in front of, my variable coefficient in front of my y is minus 2t. Right, my q of t is 5t. So in other words, I'm looking for a function such that e to the power of my constant in front of my y with respect to t is going to be my function. Okay, so what's that going to be? So it's going to be e to the power of, well, my p of t is minus 2 over t dt. So what's that? What's the integral of minus 2 over t dt? Well, it's going to be minus 2 ln t, right? I can do a little bit better than that, right? Because just by power laws, I can just take this minus 2 and put it up here with this t, raise the t to that power. So otherwise, I can change it to t to the minus 2, yeah? And t to the minus 2 is e ln t to the minus 2. T to the minus 2 is 1 over t squared, yeah, 1 over t squared. And e to the natural logarithm of something is just that something. So in other words, this is just going to be equal to 1 over t squared, right? And I can prove that to you relatively simple if I basically say y equals e to the natural logarithm of x, okay? Then this basically means that what will it mean? So I'm basically saying that natural logarithm of y, I'm just rewriting this, is equal to this power up here, natural logarithm of x, yeah, I'm taking the natural logarithm, so just rewriting it, okay? I'm just rewriting this thing in terms of, to make, the power the subject, yeah? So making the power the subject, so therefore I'm taking the logarithm to the base e, which is natural logarithm of y, equals natural logarithm of x, so therefore y equals x. So in other words, what I'm trying to say is that, so y equals x, so therefore, just plug this back into here, so I end up with x, which is y, is equal to e to the natural logarithm of x. Yeah, so that's very kind of quick side proof there. So this is what I end up with. This is my integrating factor. Mu equals 1 over t squared. Okay, so this is what I do. And so now basically what I do is I multiply every single term through by mu. So what do I end up with? I end up with mu, so 1 over t squared times dy by dt. Maybe if I write out what I had before, so dy by dt minus 2 over ty. What do we have? Minus 2 over ty equals 5t. Yeah, so now if I just multiply through by my integrating factor, I'll end up with this. So equals 1 over t squared times 5t. Because effectively the way that I've chosen the integrating factor, I get cancellation in that term. Okay, so I don't even have to consider it. Okay, so let's just look at that then. So we end up with this. So what do I end up with? So I end up with dy by dt equals okay, so what I'm just going to actually do is just rearrange that slightly. So I'm going to end up with this 5 over t then. Yeah, because it's going to be 5t over t squared. So it's going to end up with 5t. This I'm actually just going to rearrange. I'm going to rewrite it as d by dt. So I'm effectively just going to multiply through by the 1 over t, right? So 1 over t squared times y is equal to 5 over t. Yeah. So then that basically implies that 1 over t squared times y is equal to the integral of this, so 5 over t dt. So therefore that implies that, well, what's the integral of that? So 1 over t squared y is equal to, what is it going to be? 5 natural logarithm of t plus some constant coefficient. Okay, and then basically that means that y is going to be equal to t squared, so 5t squared natural logarithm of t plus c. Okay, so that's just basically how you do something like that.